In this video, we are going to talk about the stability of aromatic compounds. And to illustrate that, let's compare alkenes with the aromatic compounds. So say that we have cyclohexene in as any other alkenes. We have seen before that you can have addition reactions at the double bond, so across the double bond. So if we do that reaction, we get the following. So we're going to add across the double bond. And by the way, this is done in anti-fashion. So the two bromine atoms are added opposite sides. And we have that in other videos. So explaining why is that? It goes through bromonium intermediate. Now, but what happens is that if we put benzene under the same conditions, say that we do that in an organic solvent, such as carbon tetrachloride, and we do that, then benzene will not react. So that means these double bonds behave different ways, and we have seen that when we do resonance, that we have electron delocalization. We do resonance structures, and we can do this. Let's draw the Kekulé structure, and here, that illustrates that, well, this is a tool, a model, but what we're saying is that these pi electrons are delocalized all over the aromatic ring, so they no longer behave as the alkenes in the double bond. And so they need other conditions. For that to happen and have a bromination, actually, we need to use Lewis acid. And for example, we can have iron tribromide, and that's an electrophilic aromatic substitution, which you will learn in organic chemistry. If you haven't yet, that happens through a very different mechanism. So, but it will not react the same. In this is because aromatic compounds are particularly stable. So let's say another example. If we had, for instance, cyclooctatetraene, and that has, so 4 double bonds. So it is still a cyclic compound, but we have 8 pi electrons instead of 6. Here you have 2, 4, 6 pi electrons. And here you have 8 pi electrons. Well, it turns out that cyclooctatetraene behaves differently, behaves like other alkenes. So if you do the bromination reaction, you will have the following product. So you will add across the double bond, similar to what I wrote before for alkenes. So behave very differently. So more reactive, less reactive. So that is something that says about the, say, stability of aromatic compounds, and is related to the number of electrons. So this is something that was studied by Hickel. And with that, we have a rule to define what is aromatic compounds. So what Hickel studied was different systems that were cyclic and that were conjugated. And what he determined is that some compounds, particularly stable, will have this number of electrons. That's what we call the Hickel rule. So in these compounds, we're going to say they are aromatic if they have this number of pi electrons, and where n is an integer. And so whole numbers. And in the case of benzene, n, if you see that n equal 1, you will have 6 pi electrons. And cyclooctatetraene does not do that. So later we are going to explain that in terms of molecular orbital theory. And we will do problems about determining if a compound is aromatic, or find other definitions such as what is anti-aromatic compounds and non-aromatic compounds. That will be in another video.